This is our project on hydroelectric power and its potential to become more efficient. The question of this project is attempting to answer is what is the effect of turbine position on the energy produced by a hydroelectric power plant? The main goal of this project is to identify the most efficient hydropower plant design based on results from 3 varying turbine positions. This device should model a hydropower plant that generates the most power compared to other designs. The results from this project can be used to refine the designs of hydropower plants worldwide to make them as efficient as possible. The 3 designs being tested are a minimally used vertical design, the popular and traditional horizontal design, and a water wheel-like angular design. In each design, water uses gravity and gains momentum in different ways, which will help determine the importance of gravity and momentum in hydropower plants. To build the first model hydropower plant, a small hole was cut into one of the 10-liter boxes near the bottom of one side. Then 3 long pieces of eucalyptus wood were cut and glued to form a model ramp for the water to flow along. This ramp is called a penstock in hydropower plants. After this, the eucalyptus wood was cut to support the turbine and engine. To make the turbine, 2 circles were cut out of the eucalyptus wood with 6 smaller rectangular prisms to form the blades of the turbine, which were then attached to the electric generator. After this, a box was made around the electric generator in order to make attaching it to the support easier. The generator and turbine were then attached to support the box, and the boxes were positioned optimally. Due to a long penstock and a tall drop at the end, water is able to gain a lot of momentum and the effect of gravity on the water is large. The second turbine is very similar to the first one, except the turbine was attached horizontally on top of the support, and there is also an extension to penstock added to make the water flow horizontally. Water can gain a large amount of momentum due to a long and steep penstock, but the effect of gravity on water is minimal. The third turbine is also very similar to the first one, but the penstock in this design is wider, and a hole is cut into it to hold the turbine, effectively decreasing the effect of gravity on water and decreasing the water's momentum. To test each design, the multimeter was attached to the wires of the electric generator, and then 1 liter of water was poured into the model plant. The electricity produced was measured in millivolts. This was repeated 3 times for each design.
Each design is set up similarly, with a plastic box atop a stool. The stool is used for height, which is an element present in all hydropower plants. All designs also have the same turbine, and the way in which the turbine is attached to the electric generator is the same. In the vertical design, the penstock is 0.3 meters long and has a 9 centimeter drop at the end. In this design, the boxes have to be 23 centimeters apart from each other because of the large amount of momentum that the water has. The penstock is angled at 10 degrees. In the horizontal design, the penstock is 0.325 meters long and has no drop at the end. The penstock is angled at 15 degrees and the boxes are 13 centimeters away from each other. In the angular design, there is a hole in the penstock to fit the turbine. The penstock is 0.3 meters long and 40 millimeters wide, but the water makes contact with the turbine earlier because it is placed inside of it. The penstock is angled at 25 degrees, and the boxes are 9 centimeters away from each other.
Because the average of the highest voltages was highest with the vertical design, it is the most effective. The average highest voltages for the vertical, horizontal, and angular positions were 98.5, 87.2, and 26.1 millivolts respectively.
The results of each test were graphed on a line graph, and then the highest recorded voltage from each test for each design was averaged, and then graphed on a bar graph to compare it to other designs. For the first 2 tests of the vertical turbine position, electricity produced generally peaked near the beginning and end of each test. The average of the highest recorded voltages for this design was 98.5 millivolts. For the second turbine position, the results were more consistent than the first, but the voltage was still inconsistent. Overall, the voltage produced was lower than the first design, and the average of the highest recorded voltages was 87.2 millivolts. For the third turbine position, the results were the most inconsistent, and the voltage produced was far lower than the other designs. The average of the highest recorded voltages was 26.1 millivolts.
The results align with the originally expected results of the project because the vertical design utilized gravity in the most efficient way and the water was able to gain substantial momentum. The second most efficient design was the horizontal one, which allowed water to gain a lot of momentum, but the effect of gravity on water was less than that of the first design. Overall, the angular design was very inefficient. A general trend is that as more tests were performed on a model plant, the energy output decreased. This is likely due to the wearing of materials. Outputted voltage seemed to increase at seemingly random points, which is likely due to the varied speed at which the water was poured.
The most effective design was the vertical, due to the length of the penstock and the large effects of gravity in the design, but a wider turbine would have made it more efficient. More experimentation is necessary in order to completely conclude that the vertical design is the most efficient, because some designs had varied results and outliers. Some errors in the project are that water was not poured at a consistent rate among the tests, and the distance between the containers was not the same. A new question that arose from the data is whether or not distance traveled can make up for minimal use of gravity. The results from the experiment can be used in the real world because they demonstrated that gravity and momentum are important aspects of hydropower plant designs. Many hydropower plants have different designs, and it is important to ensure that all of them use the most effective one.
These are our references. Thank you.